Okay, so next section. Oh, and by the way, I have a cool new thing on my phone, so I can actually control this from my phone, so no, I'm not texting and teaching at the same time. That would be weird. All right, so moving on. Now we get to do some calculations with these. These are almost identical. There's going to be a slight difference. Almost identical to all the stuff that we did last chapter, okay? It's just a very specific case. It's now the cases for acids and bases, as opposed to just generic all equilibrium. And so we need to still be able to do some particular things. And most of these are actually not any different than the things that we needed to do when we did normal equilibrium. So we're going to review our weak acid and base definitions, even though you guys kind of have that. Now we're going to look at the strengths, but on the last material, we didn't give you any numbers. We just said, look at the structure, figure out the strength. Now we can give you some numbers because we know that. We have that. We figured that out. And now we can look at things like maybe we want to compare an oxoacid and a hydrohalic acid. Before we couldn't really do that. Now we can because we're going to actually look at some numbers. And then using Ka and Kb, calculate pH, and then back and forth, right? If we have pH and Kb, calculate concentrations. All the things that we did for equilibrium, we're going to do for acids and bases now. Okay, so first off, we know our difference here as compared to the calculations we already did. The calculations we already did were nice. They were kind of simple because we only had to figure out how much H plus and how much OH minus we had based on the initial concentration of the strong acid. But now we have something a little bit more complicated. We can't just say that 0.1 molar of something like nitric acid is going to be 0.1 molar H plus because it only ionizes a little bit. If it ionized all the way, or almost all the way, like our strong acids and bases, we could. But we can't because it only ionizes a little bit. So how much H plus do we really have? We have to figure that out using equilibriums. So you guys have this one. So if you want to write it down, that's fine, but you have it on a few other slides. It's a repeat slide. So for this, we have something called the ion product constant. All this is an equilibrium constant. It has a new name, it has a new subscript, but it's Kc, okay? It's Kc for a very specific case. And Kb is going to be the same thing. Now, the reason for the different subscript. One is to cue you off that it's for an acid or a base. The other reason is that when we go back and forth between Kas and Kbs, we're going to have to recognize that it's in water. And water itself has an equilibrium. And so we'll talk about all that later, but for the most part, you get to just treat this like a Kc. Okay? Just like Kc, it's products of reactants. For this, you won't really have superscripts. You won't really have coefficients. We will talk about polyprotic acids. So for instance, H2SO3 or H3PO4, H3PO3, all of those. We'll talk about those later. It's not as simple as just putting 3 hydrogens. Each one of those has their own Ka, and so we have to deal with those differently. So for the most part, you won't really have any coefficients to have to worry about at all, which is nice. Okay, let's figure out how Ka actually relates to acid strength, because that's an important thing to know. Right? We want to be able to look at the Ka of an acid or a base and know something about it. To do this isn't really any different than what we did last chapter. So let's go back a second. So if we, unfortunately I can't point with this thing, so I do have to use my computer once in a while. If we have more H3O plus and more A minus, we have more of this, it's further to this direction, what's going to happen to this number? Is it going to get bigger or smaller? It's going to get bigger, right? We have more products, less reactants, it's going to get bigger. If we have more of this, do we have more H3O plus or less H3O plus? We have more, right? We put a lot of this in, we have more of this. That means that we have a stronger or a weaker acid. Stronger. So if we have a stronger acid, this is going to be bigger. This higher part is going to be bigger, which makes our Ka larger. So the higher the Ka, the stronger the acid. The kind of analogous thing that we said to this last time was the higher the Ka, or excuse me, the higher the Kc, the more that way it was shifted, the more toward the products it was shifted. This is just saying the same thing. If we have a higher Ka, it's shifted more toward the products. Our H3O plus is bigger, So our Ka is bigger, as is the strength of our acid. So now I can give you any acids that I want, and I can ask you to compare them, and you can because you can look at the Kas. I didn't give you any Kas on this exam. You will always be given all the Kas that you need and all the constants of that sort that you need. So please don't waste any note card space on that. That will all be given to you. Okay. Now, while we start talking about Kas, I do want to mention one thing, and this is about strong acids, and then we'll pretty much do everything else in this little section with our weak acids. And that is, do they still have a Ka? What do we think? Quick shout out. Count of three. No really right. Well, there is a right or wrong answer, but I don't necessarily care if you get it. So 1, 2, 3. Yeah. So you guys are right. Do you think it's really big or really small? It's really big. And you knew that because the reaction is shifted really, really far to the which side? Right, the products. Okay. So all of that, yeah, we do have one. They're just really big. And don't even bother writing the numbers down. If you don't want, just look at them a second. So I picked 2 random strong acids and looked at their Kas so that you can see them. They're huge, right? They're big. And that's why we get to just assume that they ionize completely, and we get to deal with them as if they ionize completely, and that's really nice. They do have Kas, you can look them up, and you can see that there's a difference between them, right? Which one's the stronger acid of those 2 strong acids? Hi, right? And you knew that because the Ka is bigger. Perfect. Okay. So, example. Take a second, read it. So we need to know which one is the stronger acid between the 2. So we're going to look at the numbers on the Kas. So I picked ones that happen to have the same exponent for you guys because it makes things a little easier. So which one has a larger Ka? Benzoic acid. Okay. So which one's the stronger acid? Benzoic acid. Now, which one has the lower pH in then? Is it going to be the stronger acid or the weaker acid? The stronger. And we said which one's the stronger acid? Benzoic. So that one's the stronger acid. Okay, so for all of those, it's benzoic acid. That's handy, because we can always look up Kas if we need to. So that's really nice to know. So now we can do the exact same thing for Kb. And it's not really going to be any different. You can probably guess what I'll say before I say it all. I'm just stalling for a minute because people are still writing. Okay. So now let's look at Kb. What happens to Kb as the strength increases? So if the strength of the base is increasing, are we going to have more products or more reactants? So if we have a stronger and stronger base, we're going to have more products. So is our denominator going to be bigger or is our numerator going to be bigger? Let's do it this way. Is our top going to be bigger or is our bottom going to be bigger? Top, yeah. Okay. So since it's a stronger base, it's going to shift to the products. Shift higher toward the right. So in each case, our initial base, our combined base, our non-ionized base, is going to go down, our reactants, while both of our products, our ionized species, go up. And the important one here when we care about pH is which one? Which species are we really caring about? The OH minus, right? Because the higher the OH minus, the stronger the base is, or rather, the stronger the base, the higher the OH minus, and the higher the pH. So for a stronger base, Kb is going to be higher. So if I give you any random bases that I want, and I give you the Kb's and I say which one's higher, or excuse me, I say which one's stronger, you just pick the higher one. Again, really handy. Okay. So that's just saying the same thing in a slightly different way. So now we have 2. We have ammonia, which is 1.8 times 10 to the negative 5th. And we have something called hydrazine. Do you guys know what hydrazine is? Maybe, maybe not. I think I may have used it before, I can't remember. It doesn't matter though, because we know what the KB is, so in this case, I'm just kind of throwing out random base names. A lot of these you'll actually see and use a lot next year, but for now, it's just generic base would be a fine thing to input here. Okay, so we're asking which is our stronger base. So if we want to know which is our stronger base, we need to look for the higher or lower KB? The higher. So we're careful with our exponents here. And which one is the higher number between these two, ammonia or hydrazine? Ammonia, right, because it's to the -5th, so that's our higher number. And so that's our stronger base. Okay, so that's nice for kind of conceptual things. Of course, we want to be able to use these numbers too. And when we go to use these numbers, it's not going to be any different, right? So everything that we do here, for the most part, for like the next couple of sections, is all things that we've done before. It's just applied to acids and bases, okay? So when you go to do this one, I'm actually going to have you guys kind of try it first, because that way it'll really show you that you already know it, because you can kind of already do half the problem. Okay, so take this one. You get 45 seconds to start it. Do it exactly like you did all the problems on the midterm of this sort, and then I'll start on it. So 45 seconds, go. All right. Yeah? Ah. I want you to do the one on the thing. Sorry about that. Yeah, do this one. I'll give you another 30 seconds. Sorry, I forgot I was going to do this one up here for you guys so that it's quicker. Okay, so let's go ahead and get started. If you're not done, no big deal. You probably didn't have time to actually type everything in. All right, so we have a pH of a 2 molar weak acid solution is 3. Now, there is something that comes into play with all of this, and this is that warning that I put out that you guys need to make sure that you know whenever you're given a pH that you can find a bunch of other things from it, right? You can find the hydrogen ion concentration, you can find the hydroxide ion concentration, you could find the POH. Giving you the pH is giving you a lot of information. Okay, so our first step, we'll write out our equation like normal. Now, this is a really good, just kind of generic way of doing it. I would also recommend, let's say we give you some pretty complicated acids or bases. It doesn't really matter. You can actually use the generic version of the equation for anything that you want. This is what you need to make sure that you remember you know. That if you're given the pH or that you're given the POH, you also know how to find the H plus or the OH minus. So then at this point, it just becomes kind of doing a normal equilibrium problem. We have our ice chart. We're going to kind of treat it like a Sudoku puzzle, right? Where you fill in what you know, and then you use what you know to find more things. And you kind of work your way through the problem that way. So if we start this off, I tell you that it's a 2 molar weak acid solution. Whenever a problem says that, when it says a whatever molar acid solution or base solution, what they're talking about is how many moles you put into the solution as if you were a chemist who went over to a balance, measured out the grams, put it into the solution. It's not, that's always going to be your initial unless it's somehow indicated otherwise. Okay. The next step then is to recognize what you're getting from pH. When you get stuck on these sorts of problems, go back to the problem and say, what haven't I used yet? In this case, we haven't used pH yet. So let's say you go on autopilot for a minute, okay? You go on autopilot, you fill in zeros across, you fill in your minus x's, you go to do your Ka and shoot, you don't have it. You can't solve for x, you can't solve for Ka. It's a pretty common thing that happens. You just say, okay, what didn't I use? You go back to the problem and you say, oh, I didn't use pH. What can I do with pH? Oh, I can find my H plus concentration. Is that going to be final or let me rephrase, is that going to be equilibrium or is that going to be initial? That'll be equilibrium, right? Because initially you wouldn't have had any. Before it dissociated, you have almost none. I say almost because you'll have a little bit from water. So we can fill those zeros in, and we can fill in our 10 to the negative 3. All right, so this is the start of our Sudoku puzzle now. We have everything that was given to us filled in. Now we look at what we can find. Is there anything up there that has both an initial and a final? H3O plus, which means that we know our changes now, right? We know that all of them are going to change by the same amount. Okay, now we can find all the rest of our equilibriums. Now that we have that, we have everything that we need for Ka. Because all we need to do to be able to solve for Ka is have all of our equilibrium values, and we have that now. So we can fill that in, we can get our answer, and we're done. Okay, so now any sort of K or KB problem that is thrown at you that's similar to what we did last chapter, you can still do. All the same sorts of permutations of question asking are there, but they're all basically the same. There will be a few kind of tricks that we have to be careful of to watch for, and we'll do some more example problems as we go along. The main thing is always recognizing whether you're dealing with an acid or a base, and writing that initial equation. So if you didn't quite nail the part of the last material, the last third of the class material, on writing acid and base equations, make sure you get that down before you try doing these problems, okay? That's step one before you can do these problems. All right, so quick review. As the strength of an acid goes up, its Ka goes up. As the strength of a base goes up, its Kb goes up. So now you can rank acids and bases not just within a group, not just between the oxo acids or just between the hydrohalic acids, but between any acids. You just look at the Ks. We also know that we can do everything with Ka and Kb that we used to do with Kc. And that's really handy. The reason I didn't do a lot of problems for this is that we're actually going to be able to do something to make your calculations a little bit simpler, because our Ks and Kbs generally tend to be really, really little. And because they tend to be really, really little, we can do something that drastically simplifies most of our problems and generally saves us from having to do a quadratic equation. And for those of you who love quadratic equations, have fun, keep doing them. For the rest of us sane people, we will have an easier way so that we don't have to do it. So we'll take a couple of sections to kind of build up to that, but that's why we're not doing any right now. Okay, let's just do some kind of review, practice, putting things together questions before moving on to the next group. So some of this is kind of review from pre-exam. Some of this is just linking in the new stuff. It's just a different way of thinking of some of the problems. You get about 30 seconds on each one to kind of work on it on your own, with your neighbor, whatever you want. Okay, so for this one, which of the following is true about a 1 molar solution of a strong acid? So we have some options. There's more than one answer possible. It's a strong acid, all right? So we're going to answer these about strong acids, we'll ask them about weak acids, just to kind of make sure you have a handle on what's really happening before we start moving on with more of the math things and getting a little bit mixed up with the math. So 30 seconds or so. Oh, and E shouldn't be there anymore. E isn't an option. It was from when we had eye clickers. Okay, let's look at each one individually, because there's more than one right answer, so better to just kind of look at each one. Let's look at A first. We have the concentration of A minus is much greater, or is greater than H plus. Is that true? No, because they're going to be, can we say anything about them? What would be a true version of that? They should be about equal, very, very close to equal. Okay. So that one's not true. Now the pH is about 0. So to find that, what are we actually doing? We're taking the negative log of what? Yeah, we're taking the negative log of 1. So is the negative log of 1 0? Yeah. So it's about 0, and that's fine. We can have a pH that low. The reason I say about is that when you start getting into really, really high concentrations, you can sometimes get a little bit of the strong acid staying together, okay? So I caveated the question just a little bit to account for the fact that that might happen. We wouldn't know until we did the calculation. All right, next one. H plus is equal to 1 molar. If we break this all up, all of this, what is our H plus concentration going to be? 1 molar. So is that one true? Yeah. What about D? Is D true? If we have our HA, and it's a strong acid, so it's almost all breaking up, once it hits equilibrium, is our concentration of HA going to be high or low or 0, or can we say anything about it? It's going to be so low, it's going to be about 0. Again, I caveated myself a little bit because it's a pretty high concentration, so just in case. But it's going to be pretty close to 0, okay? Most of it's going to all split up. I want to draw attention to this one a little bit because that's a lot different than a weak acid or base. A weak acid or base is almost all of it's going to stay as HA. Hardly any of it changes, okay? And that becomes really important in the next little chunk that we do. Okay, so B, C, and D were all correct. Now we're going to do the same thing for a weak acid, so we can see the difference. The answer choice are going to be a little bit different because of it, though. Okay, so again, take about 30 seconds or so. See what you think. Okay, let's look at each of these. So first we have A. The pH is 1. So on count of 3, let me know hear what you think. 1, 2, 3. That confident, huh? Pick an answer, it's okay. Just go with what you think. All right, one more time. 1, 2, 3. All right, okay. Where did I get the answer from? Where did I pick the choice from? Why did I say it? Did I pick it randomly? What would be a pH of 1? Strong one, right? Because it's negative log of 0.1. Negative log of 0.1 is 1. So a strong acid would definitely have a pH of about 1. What about a weak acid? Does it ionize completely? Does it ionize almost completely? It ionizes hardly at all, actually. So is the H plus concentration going to be 1? No. So is it going to have, or excuse me, is the H plus going to be 0.1? No. So is it going to have a pH of 1? No. Is it going to be closer to neutral or further away from neutral? Closer to neutral. So is it going to be greater than 1 or less than 1? It's going to be greater than 1, right? I tend to like to think, and I think a lot of students do too, closer or further away from neutral when you're talking about acids or bases, because acids and bases are all kind of opposite if you're thinking ups and downs. If you think closer or further away from neutral, it's a little bit easier, I think, to not get mixed up. So that's why I choose to talk about it that way. So now, with that being said, we know that E is okay, right? pH is greater than 1. We got that. Which means that, by necessity, which one's going to be wrong? D. So we decided A is wrong because that's for a strong acid. You may even want to write that next to it so that you remember why that's not right. That's for a strong acid. And because of A, because we know that's true for a strong acid, we can say, oh, well, my weak acid is going to be closer to neutral than that. It's going to be greater than 1. So now we know that E has to be correct. Okay, so we have some left. We have B, C, and F to deal with. So let's look at B. H is much, much greater than A, and similar, B, or C, H is about equal to A minus. So if these are breaking apart, you're going to get what kind of ratio between these two? About a 1 to 1. So which one of these is going to be correct? C. I'm caveating it with the little squiggly equal signs, right? The squiggly equal signs means about. I'm caveating it with that because water does affect it a little bit, and so there's a little tiny bit of a difference. We're not really going to worry about it, but it's worth noting so that when you go on in later classes, you remember that, oh, water does matter sometimes, even if we're not going to talk about exactly when. Okay, and then our last one. HA is about 0.1. So how much was HA when we started? It was 0.1, right? We put 0.1 molar in there. And then we let it come to equilibrium. How much of there is there now? In the last case, in the strong acid case, how much was there? 0, because it all dissociated, or nearly all of it dissociated. In this case, is a lot of it dissociating or a little bit? A little bit. And it's actually probably a really, 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 really little bit. So if you take away a little tiny itty bitty 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 bit from 0.1, how much do you still have? You still have 0.1. So for most weak acids, F is true too, which is really important going forward. Okay. There's one other thing that we can say that let me pop these up real fast so that you have it if you want to write it down. So that's just what we already talked about. There's one other thing I could have put on here that I didn't. What else do we know about the pH? We know that it has to be greater than 1 because it's not a strong acid. We know something else. Where's the upper limit? It's an acid, so where's the upper limit? What would just neutral water be? 7. So if we add an acid to water, could it be greater than 7? No. So we know that it actually has to be between 1 and 7. So I didn't add that up there, but it's good to know. Okay. Let's do an example of ranking acids again. And this one's going to have both the idea that we learned when we did structural strength or molecular strength and structure of acids, as well as what we just talked about with Kas. So we have 3 different acids: sulfuric, acetic, and formic. There's one of those, and I ask you to rank. There's one of those that you do not need any more information for to rank it. Which one stands out here as the one that you can rank without any numbers? Sulfuric. And why? It's a strong acid and the other ones are weak. So we know that those are going to be higher. Now, acetic and formic, let's say that you have this in a homework question or on an exam or something like that, and you're staring at it, and you may know, maybe I draw the structure out. In this case, I didn't draw the structure out because you don't need it. Do you know what kind of acids these are? Does anyone remember? You've seen the acetic a few times. You've seen formic a few times. It's like carboxylic acid. You don't necessarily need to know that. I didn't talk to you about how to name them. I would draw them if I cared. The only difference between them is that they're both carboxylic acids. One has a hydrogen on it and one has a CH3 group. You don't know how to deal with those yet. Next year you will. Next year you'll talk about how to figure that out. They'll teach you some different ways and some more additional ways than we talked about. For right now, we don't know it. So what do? You look up the Ks. Remember that you can always look up the Ks, right? Don't sit on a homework problem like this forever and be like, I don't know how to do this, I don't know how to do this, I don't know how to do this. Just go look up the Ks. On an exam, you just go to the front page and I'd have all the Ks listed. I generally don't put the Ks on the questions where you need them. It's a little bit too much of a giveaway. I put them all on the front page in a giant chart for you. Okay, so you look up the Ks of these. You know that your high K is your stronger acid. So you're given the Ks now, so I'll put them up here. So in this case, which one's our stronger acid? Yeah, formic. Okay, so just kind of connecting the two different things we did. So there are times when you should be able to rank them on their own, okay? Things like strong acids you should know are stronger. Within an oxoacid group, you should still be able to rank them. Within a hydrohalate group, you should still be able to rank them. Within a carboxylic acid group, you should still be able to rank them. All right, so things we remember, things we know we know. Our strong acids ionize completely, and this will tell us something about weak acids, right? We can use the calculations that we did with strong acids to give us a range for our weak acids. So we were able to calculate, oh, this random weak acid that we don't know anything about has to be between pH 1 and 7. We also know, and we didn't talk about this in this section, I just want to remind you of it, and I'm using this little review section as a reason to do it, that when you're at identical concentrations, your strong acid is always going to have a pH further away from neutral, right? So if we're talking about an acid, our strong acid is always going to have our lowest pH. Our strong base is always going to have our highest pH. However, that doesn't mean that always and forever, if you have a weak acid and a strong acid, they're going to have the pH that the strong acid is always lower. And I did that example up here, right? And I want to kind of repeat that a little bit because that's important. So that was when I had the 2 beakers and we started off with the same concentration and we had pH paper that changed colors. And at the same concentration, the strong acid was super, super low. It was like a pH 1. How did I make that strong acid have a pH closer to neutral? What did I do? I diluted it. I took a tiny drop of it and I put it in a bunch of water. I diluted it. So a really dilute strong acid can still have a pH of 6. It's just got to be pretty dilute. Whereas you're going to have a pretty concentrated weak acid in order to get it to go down to like 1 or 2. I mentioned this not just for the sake of our calculations, but there's a safety issue involved here too, that if you walk into a lab and you see a bottle of, let's say, concentrated acetic acid, well, and you say, oh, I know acetic acid is a weak acid. It's not going to hurt me. And you don't wear gloves, or you do wear gloves and you're sloppy, and you burn yourself, a very concentrated solution of a weak acid will absolutely burn you. So keep that in mind too. I think, if I remember correctly, in like Breaking Bad, they use like HF to dissolve a body, and we know that that's the weak acid. So just because something is weak, it doesn't mean that it's not very low pH. So keep that in mind. Okay. This is going to seem like a little bit of a random insert here. Here's why we're going to talk about it here. Technically, it's just saying, we know what the definition of a percent is. It's the thing that we're talking about over total times by 100. The reason I'm choosing to talk about it here is we're going to use a concept based off this to help make all of our math easier, and so I chose to put it here. We're going to define percent ionization. It's not actually any different than just percentages. It's the percent of the thing that's ionized, or the thing that's ionized, over total times by 100, right? we'll actually go through and calculate percent ionization a few times, because you do end up having to usually make an ice chart to do it using Ka. And so we'll go through an example of that. The important part here is to, one, recognize that this is actually a different way of talking about strengths of an acid. It's not the same as Ka or Kb, but it is a different way of talking about the strengths of an acid. And also being able to calculate it so we can use it later on. So it's just a different way of reporting a strength of an acid. If it's more ionized, are we going to have more H plus or less H plus? More. So the higher that percent ionization, the more it's broken apart, the more H plus you have, the stronger the acid. Now, we don't report percent ionizations in tables. And the reason for that is it changes based on the concentration. Think back to like maybe the first day of class, something like that. And when we were talking about KCs, and we said that the reason we use KCs instead of ratios is they don't change. That regardless of your concentration that you started with, your Kc doesn't change. And that's why we use Ks and Kbs too. Percent ionization is going to change based on your initial concentrations, and it's not useful as a reporting constant because of that. But we can still do other things with it. So this will just be however much is ionized, which means it's the equilibrium value, right? However much that at equilibrium has been ionized over top of the total. Right? Just like percent on an exam is the number you got correct over the total. Percent of anything is the number of things you're talking about over the total, times by 100. Okay. So let's say we have something like nitric acid. We're going to take the amount of nitrate ion that we have at equilibrium over top of the nitric acid that we started with. So maybe you want to add in your notes here too. This is your equilibrium value, the amount of that at equilibrium, because your initial amount of it's 0. So it's got to be your amount at equilibrium. This is your initial value, okay? That's what the little naught means. So at equilibrium, initial. The amount that ionized over how much you started with. So we're going to do this with just the picture first, so that we don't get lost in any of the ice charts or any of that first, just so you get the idea. And then we'll do a slightly more complex version. Okay, so we have this little picture with our giant molecules that fill up an entire beaker. That's fine. Let's do our percent ionization for it, okay? So we go through, we count how many break apart. I highlighted them so they'd be easy to see. We broke apart 3. If you count up how many we had total, we have 14. You can trust me on that, or don't trust me and count them later, whichever you want. So we originally had 14. When we got done, we had 3 broken apart. Now, yeah, that means that we have 11 that are still together. I didn't write that number down because it doesn't matter. What we care about is how much we started with and how much dissociated. So that's a 21.4% dissociation. Okay? Amount dissociated over initial amount, that's your percent dissociation. Now, obviously, this is a little bit of a ridiculous example because you're never going to have just 14 molecules inside a beaker. To put that in a little bit of perspective for you, there are more atoms in a single grain of sand than grains of sand on the Earth. It's kind of a lot. So that's a ridiculous example. Keep that in mind. So when we go to do this for real, we're of course going to do this with molar, right? We're not going to count atoms. But that doesn't change anything. We're just using moles instead of atoms because, you know, this is a lot of numbers and we don't want to have to deal with exponents like that. It's good to remember why we have moles sometimes too. This is also my reminder of why we have moles. Much easier to deal with than if we have to deal with numbers. We get really used to saying, 6.02 times 10 to the 23rd, and we never really think about what that 10 to the 23rd number is. It's huge. Okay. So let's real quick actually state this on a slide, even though I kind of already mentioned it. How is this related to Ka or Kb? We've talked about each individually. So if the strength of an acid increases, what happens to Ka? Increases too, right? Higher strength means it's shifted more toward the products, more are broken apart, and so higher Ka. What does it mean about the percent ionization? If you have a stronger acid, it's shifted more to the products, you have more H+, more A-. What does that do to your percent ionization? Makes it bigger too. So as something goes up, both your Ka and your percent ionization goes up. So what does that mean? Are they directly related or indirectly related? Yeah. So in both cases, as your percent ionization increases, your products increase, your reactants decrease, and so they're both going to go up. You can't say that it's always going to be like a square or always going to be ×2 or something of that sort. You can kind of do it, but it doesn't really work. So all I really want you to know is as one goes up, the other one goes up too. So if I were to give you the Ks of a couple of acids and say which one has a higher ionization, you would know, oh, it's the one with the higher K. I'm going to say that one more time because a lot of people were writing as I was talking. So if I were to give you two different acids and I gave you the Kas and I said which one has the higher ionization, you're going to say the one with the higher Ka. Okay. So quick review. We'll do these in many problems. You'll get lots of practice at this. So to calculate our percent ionization, we put our amount at equilibrium of our ionized species over top of our total amount. Notice, did I use H+ or did I use A-? I used the A-. There's a couple reasons for doing that. Sure, theoretically, you could kind of use either one because they're about the same. But generally, we talk about it being the A-. Bit of review, what's another word for that? Instead of saying A- and calling it generic, what else could I call it? It starts with a C. I could also have said the conjugate base, right? So we put the conjugate base over top of the initial acid. Some review of terms. The higher our percent ionization, the higher our Ka. Or, if we're talking about bases, the higher our percent ionization, the higher our Kb. And now we get to use this. So this next section is going to be talking about how we get to use this going forward. Okay. Let's do more problems on how to do weak acid and base problems. But now we have this percent ionization in the background, and so we can add something in when we do these more complex problems called the weak acid approximation. And this helps us out quite a bit. So it's why we saved some of the more difficult problems until after that last section. There's things you need to know before we can do this. So this is me reminding you of what you either do know or what you need to make sure you know before you do these types of problems. As a general study guideline for math and sciences, you should never skip to the hard things before you learn the fundamental things. You'll waste a lot of time not knowing what you already kind of have in the background. So make sure you know how to do percent ionization, okay? So it's just the amount, if you already have your ice chart made, it's just that conjugate acid or base over top of the initial. Use ice charts and Ks and Kb's equations to calculate various concentrations, calculate Ks or Kb's, all the different varieties of that we learned last chapter. And then finding K equations. So actually that middle one really should say Kc's, just because we're going to use the same problem solving techniques as Kc's. So now what we're actually going to do is what I claimed in that middle one. We're going to use all of those materials, put them together, and do this for acids and bases. But exact same problem solving techniques as last chapter. So there's going to be a lot of different ways of going about this. I know one of the most commonly asked questions that I didn't really answer each time from last chapter was, I don't really know how to go about doing these equilibrium calculations. And there is not one answer for that. The problem is that there's about 15,000 different types of ways we can ask the questions. And so you need to look at them very holistically. Look at what you know, look at what you don't know. The ICE chart is not a magical problem-solving technique that cures everything. It's a note-keeping technique. It's really just a really clear-cut way of organizing your thoughts. For those of you who come to office hours a lot, you saw I tend to always think down I start with an equation and kind of think down a row all the time. ICE charts are just a way of kind of teaching that to you guys. Now, the other thing that we're going to learn how to do is actually use the approximation to make your calculations simpler. For those of you who rely heavily on the book, you saw this last chapter actually. I don't tend to teach it with equilibrium because with equilibrium, it doesn't happen super commonly. It happens a fair amount and it's nice when it happens, but it's not really common. With Ks and Kbs, it's super common. So I think it's better taught here where it really saves you a lot of work. Last chapter, it only saves you a little bit of work. Here, it saves you a lot. So we're going to use this approximation, and then we're going to check to make sure it's valid. Anytime you make approximations, you have to make sure it's valid. Okay, so we'll go through this really quickly because you kind of already got it in one of the earlier questions. But if we have this set up again, right? This was how we talked about equilibrium to begin with. We had this game, in case you weren't here that day, we had this game where me and my friends, who are all super not good at throwing, against the Avengers, who I assume can throw pretty well because, you know, they're superheroes. And when we started this whole thing, we started my team out with 10,000. It's kind of an unfair situation to begin with. And we started throwing them back and forth. And we let the simulation run. And no matter what happened at the end of the game, at the end of the time, we always had about 10,000 and they had about 3. Okay, basically because it took them, you know, half a second to pick up the ball and throw it. The reason why I want to go back to this is I want to show you the difference in the numbers. So let's say they have 10,000, or I had 10,000 when I started off. How many do I have when I end? About 10,000, right? Okay, that's pretty much the same number. The difference between 10,000 and 9,997 is basically the same number. Is the difference between 0 and 3 the same number? It's pretty different, right? If you had, so we can think of this a different way. Money is another good way to think about this one. So I have $1 million. I don't, but let's claim I have $1 million. And I come over, and I'm going to give you $1 million. Yeah, you take it. Is that a lot of money? Yeah, you want that, right? Is that significantly changing your life? Yeah. Okay. Now, my good friend, I usually use Bill Gates, but no, he doesn't come up later in this class, so I'll use him again. Okay, I have Bill Gates sitting right here, okay? I walk up and I say, Bill Gates, I'm going to change your life. Here's $1 million. And he laughs in my face. Why? I gave her $1 million, and trust me, she was really grateful. She's just shy. Bill Gates laughs in my face. What's the difference? It's $1 million, just like that's 3 and that's 3. $1 million to Bill Gates is nothing because he has so much already. $1 million to, I'm gonna caveat this a little bit, probably most of us in this room, is a lot of money, right? So keep that in mind when we get to choose when to use this or not. It's all about how much we're changing in comparison to how much we have. And that'll help you realize a little bit more than just randomly filling into equations and then deciding whether you can use something or not. So the idea here is always you have a bunch of things, a lot of HA, it's staying together, it's almost all together, it's almost all as HA together, but just a little tiny bit changes. Now, again, we're remembering that this is like a really scaled down version because I can't draw, 10 to the 23rd molecules, but keeping in mind that most of them are together. Most of them are staying connected. What this ends up meaning is that for things that have very, very small Kas, for things that are almost all HA together, or very small Kbs, so the Kb hasn't really picked up the hydrogen at all, the amount that you start with is pretty much the amount that you end with. It's the Bill Gates example. It's saying that $1 million to him isn't even a drop in the hat. So he was worth, X billion dollars when he started. He's still worth X billion dollars. All right. So if our Ka is small, our equilibrium lies really far to the left. That's not new, right? We know that. I've kind of drilled that one into your head with about 15 different slides. That means it was pretty much all HA together. Very, very little of it is H plus and A minus. And that means that the HA doesn't actually change that much. However, the H plus changes and the A minus changes because they had nothing, they hardly had anything to begin with. I don't want to say nothing because they could actually have a little bit, but. So it's all relative, right? $1 million to me is a lot. $1 million to Bill Gates isn't. So, 1 times 10 to the negative fifth is a lot to the H plus, but it's very little to the HA. A way of putting this in math is just to say that our HA at equilibrium is about the same as our HA naught. So the words is pretty much the exact same thing as what that little equation means, just depending on how you want to look at it. Okay, so let's do an example. And I don't actually necessarily care about you doing the math on this example. I'm giving you the math. I'm just handing it to you. And the reason why I'm doing that is because I really just want to point out a couple of things rather than actually work through the problem. So let's say we have a 1 molar acid solution, and I give you the Ka. And I tell you that at equilibrium it has this. What's the final HA concentration? The point of this is not to do the problem. The point of this is to look at the answer. So if we do this out, this went from 1 molar to 0.99576 molar. We round that to proper sig figs and we have what? 1. All right? It doesn't change. Sure, it changes a little bit, but that little tiny bit doesn't matter. Okay. Now this went from 0 to 4.24 times 10 to the negative third. It's technically the exact same amount that this changed. But this one matters because it didn't have anything to begin with, right? That's someone walking up to me and giving me $1 million. This is someone walking up to Bill Gates and giving him $1 million. This doesn't matter. This does. And if you look at how it's going to get filled in to the Ka or the Kb equation, you can see why it would make a difference too. Because this is going to be on the numerator, right? So you're going to have this multiplied by this, divided by that. So otherwise it would just be 0. So that little bit does matter. Okay. It's approximately the same. Now that we have the reason for why we can do this kind of fully in our heads, I want to talk about when we can't. Because there are times with weak acids when we may not be able to. So let's look at this graph. A good way to read graphs, if it's the first time you've ever seen it, start at 0 and think about what that means. Or start really far out and head to 0 and think about what it means. In that case, we're going to do the latter. So we're going to start out here. We know that generally a weak acid has a low ionization or a high ionization. Low. Good. So this generally has really low. So that's what we're seeing out here. Out here we're seeing that at a high concentration. So this is our initial concentration of acid. At a real high concentration, we don't have very much ionized. That's out here everything that I've told you up until now. Now, if we start lowering the concentration, and we lower the concentration, and we lower the concentration, what do we start noticing when we get to about here? What happens? It starts increasing. So if you lower the concentration, your ionization starts increasing. There are times where this weak acid approximation doesn't work. The weak acid approximation doesn't work if you're almost all ionized. Now, we're so used to saying, oh, well, weak acids don't do that. That's true most of the time. But if you're at a really, really low concentration, they will. And also, by calling them weak acids, we're assuming that their Kas are really low. But the Ka, if it's kind of borderline, we do have some acids that are kind of borderline. Actually, acetic acid is a good example of that. It's definitely a weak acid. It has a Ka of like 1.8 times 10 to the negative fifth. It's not super, super, super weak. So that can come into play too. This balance between Ka and the concentration is important for knowing whether or not you can use this approximation. Okay, so there's two ways to know if you get to use it or not. And for the first, all of the acid-base equilibrium problems, I am going to require you to check it and to show me if you'd use it on an exam in the work. I'll even have a little place where I say, approximation check if used. That being said, you never have to use this. When I was in your class, I was pretty good with quadratics and I didn't really mind doing them. I just did the quadratic all the time. So that's fine, you can do that. It's just a lot more work. So here's how you know if you can do it. We've decided, and by we I mean the general chemistry people who have decided this a long time ago, that if you have a percent ionization of 5% or less, you can use this. There's a catch-22 here. If you haven't done the calculation yet, are you going to know what the percent ionization is? No. So what you end up doing is you do the calculation, you do the approximation, which I'm going to show you how to do eventually. I won't leave you hanging there. And then you check it, and you see if it worked. If it worked, yay, move on. If it didn't work, go back and solve the quadratic. Now, that being said, there's another way that you can check it before you ever do the problem, and it's pretty good. And that is to take this graph into account and your K into account. And say, well, okay, I know that if I have a really, really high concentration of acid, I'm fine. If I'm way out here on this graph, it's not going to be ionized very much. And since it's not ionized very much, I can use the approximation. So I need a high concentration. Also, I need a low Ka, because if I have a low Ka, that means that most of it's going to be together and not ionized. So then I'm okay. So what this ends up becoming is you say, okay, well, if my initial concentration is about 1,000 times bigger than my Ka, I'm okay. So if you have a Ka of 1 times 10 to the negative fourth and a concentration of 0.1, you're probably okay. If you have a Ka of 10 to the negative third and a concentration of 1, you're probably okay. So it's true at low Ks and high concentrations. How many, just quick show of hands, have done these sorts of calculations with the 5% rule before? Okay. Okay, this is a slide mainly for you guys. I'm not probably going to give you time to write it all. Just go ahead and pull it down from the internet if you want. So your steps for doing all of these problems, it's not really any different than your other ones. Write out your equation. Make your ice chart. Turn this way. Make your ice chart. Fill in everything that's obvious that you know. Then go back and do one last check on your problem and see if there's any information that they've given you that you can use and you haven't. Usually this will be pH or POH, something like that. And then put that in if you can. At that point, it becomes like all your other problems, where you're filling in whatever you can find out. So let's say you end up, once you fill into your ice chart, you have an initial and a final concentration of something. Now you know your changes, and you can find all your changes. Or maybe once you fill into your ice chart, it turns out that what you're actually given is all initials in a change. Now you can find all your other changes and find your finals. It's like a Sudoku puzzle, almost in an actual literal way, right? Especially if you have me for 1A, I've used that as like a kind of catch-all for logic puzzles. In this case, it really is almost literally one of those Sudoku puzzles, because you are just filling in what you know, using what you don't know, or excuse me, using what you know to solve for the in-betweens. Okay, so let's do a problem. So we have formic acid, which is HCOOH. I wrote it a little differently here just because sometimes they write it like this and it's worthwhile to see the different ways that they write it. One of the ways that they can get this, the place that they first found it, is actually from ants. That's where the formic part of it comes in. So if you have a 0.1 molar solution of formic acid is isolated, what is the pH? So I'll draw it out so you know what it looks like, even though you can kind of see it in the structure. First step, we'll make our ice chart and fill in what we know. We're given this 0.1 molar. Assume that it has a few more significant figures. I'm going to throw in a couple more sig figs there for you. Yeah, that's better. Okay. I know we aren't harping on sig figs in this class really at all, but it's still good to kind of throw it in there. Now, we know our 0, 0s too, right? Remember, if they tell you the solution of formic acid, they're telling you the initial concentration. They're acting as if you have walked into a lab, you have measured out the grams, you have put the grams in the beaker and mixed it up. Now, we can go ahead and write our changes. We don't know what they are, but we know that they're a 1-to-1-to-1 ratio. And we know the species. We know what we're talking about. We know which acid we're talking about. That's important to recognize too, because if we know what acid we're talking about, what else do we know? We know the K. So if we can go look up the K, we can go look up the Kb. It's important to know if you know the acid or not. So it's probably not going to be a problem to do the minus x's. Where the minus x's become a problem is if you don't know the K or Kb. But in this case, we do. So we go look it up, and we have that. You may want to put a little note on that number, looked up, right? So that later on you're not saying, where did that number come from? And now we have our K equation, just like normal. And here's where the weak acid approximation comes in. We say that that 0.1 minus x is still about 0.1. Okay? We say that if you take away 0.1 from x, you are basically not taking away much of anything. And it just becomes 0.1. Notice you can't say that the x doesn't matter, because if you say that the x doesn't matter, now you've just sent the whole thing to 0. That doesn't work. That matters. Well, that's a much easier calculation, right? Because now instead of solving a quadratic, you just multiply the 0.1 up and take the square root and you're done. And you get this. Much easier math. I'll give you a second to write because we went a little quick. Okay. I just moved it up and took away some of the work. We're not done yet for a few reasons. One, we haven't actually solved the problem. What did I ask for? pH. So since I asked for pH, what number do we need here to tell us pH? H plus. And since I have H plus, or I have X, I have H plus. But we made an assumption that that X was little, and we need to make sure that that was legitimate. And so what we do is we do an ionization problem. We just say, okay, what's my percent ionization? That wasn't too bad. Remember that one from the last little section. You just take the amount that's ionized, in this case the conjugate base, and put it over top of the initial value. And that's what we have here. We have X over 0.1. Two different ways of thinking about this, depending on whether you tend to be really conceptually minded or whether you tend to be really mathematically minded. The conceptually minded way of thinking about it is what I just said. That you're taking the conjugate base, you're taking the ionized amount, and you're putting it over the initial value. If you tend to be more mathematically inclined, and you just kind of like playing around with equations, here's the other way you can think of it. I said that this is really little in comparison to that. So I took x divided by 0.1. Okay? So you have the idea that you have this conjugate base over top of your initial value, and you're finding the percent ionization. And it's got to be less than 5%. Conceptually minded, x over 0.1. Mathematically minded, oh, this is little in comparison to that. So I'm going to put x over 0.1. Either way, you're putting x over 0.1. And you get your number. It's 4.2%, so we're okay. Now, if you're saying, well, why 5%? Like, isn't that kind of close to 5%? We have to draw the cutoff somewhere. If you were doing something that needed super exact precision, really, really on the dot, would you use this approximation? No. It all comes down, when it comes to these sorts of approximation, all of life is about, well, how much do you actually care? Or how much does your boss actually care? Or how much does this particular reaction actually care? And so for Gen Chem, we've just said 5% is good enough. Maybe later on for certain reactions, that won't be good enough for you, but that's fine, it's up to you. So what this little check does is it says, okay, we were right to use the assumption. We were okay to say that x is really, really little in compared to 0.1. So we can keep going. So you take your negative log of your x. Why did I pick x again? Why did I do negative log of x? It's our H plus concentration. Be careful when you go to do bases that you remember that that's actually your POH, so you have to do an extra step. We'll do some of those too. So you get this. Let's check and make sure it makes sense. It's an acid, so should it be greater than or less than 7? Less than. It's a weak acid, but it's pretty concentrated. You may not have a feel for that yet. You know it's got to be less than 7, and it is. But I would also maybe suggest looking at things and saying, well, if it's 0.1, it's pretty concentrated. It's probably going to be relatively low, even if it is a weak acid. You can also see why numbers that seem a little low in lab, we still really care about your safety on. That's a 0.1 molar, right? Things you're dealing with in lab are definitely 0.1 molar. It's a 0.1 molar of a weak acid, and it's still a pH 2.37. So don't let numbers like 0.1 make you think that acids aren't a big deal still. Okay. Let's do another one. Right away, I want you to notice something about this number. So here I have 0.005 molar ammonia. So first question, what's the formula for ammonia? NH3. So is that an acid or a base? It's a base, right? That's our group of nitrogen with 3 bonds to it. We're recognizing that as a base. All right. I wrote this out as a full equation. If you tend to like general equations, because I know sometimes that's useful to have, usually the general equation we use for a base is to write B plus water goes to BH plus OH minus. So if you wanted to do it really general, you could do. So it's been a while since lame chemistry joke time, so you get one. Do you know why we like using ammonia so much as like examples? Pretty basic stuff. Yeah, it's totally deserved. That's the laugh it deserves, but I like it anyways. Okay, now everyone's had time to write things down. Bad chemistry jokes are great stalling techniques. Make a nice chart. Okay. We fill in what we know. Oh, there was one other thing we were supposed to notice. 0.0005. It's pretty small, right? It's a little small. When do we know we need to start being concerned about whether our weak acid approximation is true? Is it that we have to be worried at high concentrations or low concentrations? You have to be worried at low concentrations. So we may want to think about this one a little bit and say, oh, maybe this one won't work, maybe it will. It's going to be a little more iffy than the other ones. But let's go ahead and do it as if we're going to assume anyways. So we fill this in. And we fill in our minus x's. And we fill in our equilibrium. We know our species, so we can go look up the KB. So again, if it helps, you may want to write looked up next to it. Happens to be the same number. And that's our KB value. Okay, so if we do the exact same thing that we did before, and we're going to. Now, there's something else we can kind of compare here. We can say, well, this 0.005 is actually pretty close to the 10 to the negative fifth. And maybe this is the point where you say, you know, I think I'm just going to solve the quadratic and not bother making the assumption because it's kind of on the borderline. Maybe you say, nah, it's not going to take me that much extra work. I'm just going to make the assumption and see what happens. That's completely up to you guys. So we solve for x, and we get 3 times 10 to the negative fourth. Now, it's a pretty small number, but we were subtracting it from a pretty small number. So when we go to look at our assumption here, again, 2 different ways of thinking about it. We can think about it as the ionized species over top of 0.005, right? It's kind of conceptually minded, what's the percent ionization? Or we can think of it as, oh, this is going to be really small in comparison to that. Either way, you end up with x over 0.005 or x over 0.005. I wrote this way, so I wrote it as the concentration of this over the initial concentration of NH3. Yeah? Yeah, so if you want to write in another step here, put a little caret over here and write x squared over 0.005, right? So right here, x squared over 0.005. And that's the sort of in-between step there, where we just say, yeah, we're assuming that x doesn't matter. Anytime you do it, you got to check it, though. When you're doing it in your homework, you can just type it into your calculator. When you're doing it for me, I do need to see it because I don't have access to your calculator logs. Okay, so we do that, and we find that it's 6%. Is 6% less than 5%? That was an easy one. Is 6% less than 5%? No, so our assumption isn't valid. Now, you know, maybe you're in a lab, and you're doing this for something, and you know that it doesn't matter that much. Sure, maybe this would be okay, but we've put our line at 5%. So we can't do this. Not a big deal. We just go back and we solve the quadratic. So we're a little out of order, but that's all right. So we go back, we fill into our quadratic, we solve for our x. By the way, you don't necessarily need to write this quadratic down, right? You guys know how to solve quadratics, so the important part is just the x. Now, you might say, so we made that assumption, and it made our life easy on the first one, but on this one, it actually added like 2 or 3 steps. That's true. So don't do it if you don't want. In general, it will save you time. As a general rule, it will save you more time than it costs you. That's especially true if you learn to recognize these times where it really matters. These times where your concentrations are small and maybe it doesn't work. So that's why on like the last slide when I was talking about this problem, I said, hey, this might be one where you say, you know, my Ka and my concentration are close enough to each other that I don't think this is going to work, and you just solve the quadratic. Maybe you just always solve the quadratic. Or maybe you go ahead and do this and you find out that it doesn't work once in a while, and every once in a while it costs you an extra couple of minutes. Either way is fine. Okay, thing I want to point out as finishing up this problem, notice that I had to do this extra step, right? This is where making sure that you always say to yourself, does this answer make sense, will catch mistakes. Because there is a habit of just putting a negative log of the thing and then leaving it. So if you look at this and you say, well, I have a base, does a pH of 3.56 make sense for a base? Nope. And so you would remember, oh yeah, I solved for the pOH right now. We're not quite done yet, guys. I solved for the pOH right now. And so, therefore, I need to actually subtract it from 14. Okay, for these, take like 5 minutes tops and actually try to do it before next class, okay? So it shouldn't take you very long because they're very similar to what you did on the exam and you guys rocked the exam. So just take 5 minutes, try to do them, and then I can go through them a little bit faster next time. All right, see you guys next time.